Okay, so the last part of attention, they call this self-attention. Self-attention and intra-attention were used kind of interchangeably at the beginning, but then self-attention moved on in the literature to mean what we're going to talk about today. So keep intra-attention for when you're paying attention to the sequence you're generating or reading, but a single sequence, and self-attention to mean exactly what we're going to talk about today. So this is transformer architecture. How many of you are actually familiar with this? Now that you're here, I can ask this. Okay, some familiarity. Okay, so all transformer architecture is a parallelized version of your attention. That's all it is. So it's a smart way to parallelize your recurrent neural network. Why do we want to do that? Because in neural network, especially when you're decoding and encoding, a good chunk of time is consumed by waiting for words to be processed, because you can't read the third word if you haven't read the second word, for example, in an architecture. Right? If you remember the states, they have to talk to each other, so you have to go back, you have to check the information from the previous state to be able to construct the current state, right? And then that they cannot use our powerful tools such as CPUs or clusters. It just cannot optimally use those types of technologies, which results in a longer time and less parameters being trained. Right? You want to be able to train more parameters. So that's all self-attention does. And to give you the endpoint right at the beginning, it does it by constructing representation for words. So each word at any point in time can separately be trained on a set of cores in the GPU or a separate GPU, such that it has all the information of every other word in the sequence. So it's completely independent of everything else in the sequence. So each word representation in your network is a summary of your entire sequence. Why is that helpful? Because that word is a weighted representation of the entire sequence. So if you remember attention now, that word is an attended over representation. All it is how other words relate to it. And it has all the information in a summarized manner, in a form of a vector, right? Okay, so you'll see quickly in a second. So basically, you have in your transformer network, you feed in your French. Let's say it's a translation task. It does self-attention. But self-attention is each word separately and independently pays attention to every other word. So it's kind of a separate network of its own. And then you can, for that reason, you can parallelize it. So your entire second will run in an instant, because all of the words are being processed at the same time. You don't have to wait for the first word to be processed. You have some sort of representation called Z, and you pass it on to a feedforward network. So this is your encoder. So let's talk about the self-attention layer. So you have an input in your item in your input sequence. You have a representation, intermediate representation out of the self-attention. So that's the weighted over representation. And your Y is your output. So you can have 6 encoder and, well, in the original architecture there were 6 encoder and decoder layers. And when you say layer, it's a combination of attention and feedforward. All of them together is a self-attention layer. You see the box? So we call the entire thing a self-attention layer. Well, yeah, a transformer layer. Taking self-attention is this guy, and then your feedforward is this guy. All right. And dimensionality of your embeddings are 512, as the output. 2 types of sublayer, as I mentioned, self-attention and fully connected. And then you normalize it, and you have a skip connection. I think I have skip connection. Let's see if I have it. Okay, I do not have it, so let me tell you about it right here. So basically, when you do all this, you want to, before you normalize, you want to bring in the original representation as well. It's a deep architecture. What we noticed with deep architecture, remember about vanishing gradients? You will see when the architectures were so deep, layers and layers and layers of computation, and a lot of times the network just forgot what it was. Like when you get to a point where when everything becomes zero, right? So if everything is zero, your gradient's zero, you're not really improving anything. You don't get a signal, right? So your network stops learning because it stops generating useful output. So a remedy to that was to bring in information from previous layers, because my nonlinearity, my nonlinear operation, be it sigmoid function, tanh function, can bring things to places that are undesirable. So we skip the nonlinearity as well. We bring in, we exactly copy the previous layer's output before going into the nonlinearity, before going to the sigmoid function, and we add it to the output of the sigmoid function. So you have both. At least if the sigmoid function got completely lost, you at least have a representation from the previous layer, right? So that's the skip connection, and it's actually written here. So your x is your input, and then sublayer of x is technically your output of this sublayer. And when you add that connection, when you add these two, it means that you have an arrow coming from this guy to this guy, for example, as this is the output of the sublayer. And the dimensionality of your feedforward is 2048. Your input outputs are 512. Okay. So this is how you get your sort of mean and standard deviation. Why do you need them? 4 layers, so you should get your mean and standard deviations for each layer to normalize your layers, right? To normalize the outputs of your layers. We want things to stay within a range, right? And basically what you do is you just center things by subtracting the mean and bring it to unit variance by dividing by standard deviation, right? So it does it. It's used in transform network. All right. So you have 3 keywords. In the interest of time, I'm gonna say this quickly. We will get back to it if you have questions. I figure that's the best way to teach this type of material. So basically, you have your keys. You have Q, K, and V, right? Q is called query. K is your key, and V is your value. And it doesn't really matter what they call, or because they're all initialized the same way. What matters is that we use Q and K to create a weight between 0 and 1, and then use that as the attention and multiply that by V. Why is that important? Because they can easily parallelize it on the GPU. Again, you don't have to, in the normal attention, you have to wait for the entire sequence to go through. Then when you have the entire sequence, you would pay attention and you would create your attention mechanism, and then you would multiply the attention, if you remember, the coefficient by all the representations of H1 all the way to the last, 0 to the last. Anyhow, so you have your words, thinking machines, for example, and then you have your query K and key and value matrices. So you see that these matrices will learn how to generate. At first, they can initialize. You can initialize them in the same way, but later on, you can actually they will learn how to generate keys. How keys should be different from queries. And again, so key is query is if you have an utterance, if you have these 2 words, you want to get the representation of thinking, then you query thinking. Okay, we'll get to that in a second. I guess a little bit more there. Okay, so let's say your operation is thinking machines, and you want to send that to a GPU to work in parallel to get an attention-based representation for your word thinking, right? All you do, so you have your query key and values for thinking. You basically get the dot product of your query and key, right? So you get a score, non-normalized. Then you normalize it. This division, and don't be too much distracted by it. It doesn't really matter. Is because your attention is using the dot product. What that means is that the bigger your vectors get, the greater the value will get. You want to normalize it by the size of, relative to the size of your vector. So that d is the dimension of the vector. What that will do to your entire training is, if you don't do that, it will move your gradients towards regimes that are very small in gradient, so that they won't be useful. You won't be able to train your machine that well. Simplistically said, it just generates noise, and you want to get rid of that noise. So you just normalize it. So that's what the division is, but it doesn't really matter. What matters is that you have your softmax layer. You know what the softmax layer is, right? We went through this. So you have a softmax layer that gives you a probability. We love probabilities because then you have probabilities for 2 words. So it's how much attention for the word thinking needs to be put on the word machine. And you see, now here you can understand the difference between now queries and values. As I said, when you want to get the representation of the word thinking, you use that query, you use that word, the Q of that word. Use the Q of the word on itself. How much should I pay attention to myself? Okay, fine, pay a lot of attention to yourself, 88. For machines, how much should I pay attention, how relevant they are, or however the machine thinks about it. And you use the query of the first word and you use the key of the second one. That's why you have query and key. It's just a way to connect things, connect words together. Now, if you want to get a representation for machine, which query you use, please raise your hand. Let's say you want to do the other way. You want to get the representation of machines instead. Do you use Q1 or Q2? Who thinks we should use Q1? Who thinks we should use Q2? Okay, thank God. Okay, okay, good. Yes. So use Q2. Use query 2 because you want to query the representation for machine for machines, right? And then depending on which relationship you want to figure out, you want to see its relationship. It's how much it pays attention to word thinking. You use the key of that word. So this is a 2-word sentence, or phrase, but it can have an entire sentence. And you can see how we can imagine that. And after that, you get your softmax value, and you multiply your softmax by your value of v. So that's why we need v. That's why we have these 3 vectors. Because okay, you got your attention. Now what? It's a scalar. What do you want? You don't have a representation. As I said, a lot of methods in NLP, you need some representation to use some cosine distance, or some understanding or classification, what have you. To get that representation, I use the values. Now, which value should I use? Well, every value, because as I said, every word is a representation of every value, every other word in the sentence. So you get every value. You gather all the values, value vectors, and if you remember, the value vector was separately generated by a grade matrix. You get all the value vectors, and you multiply their corresponding attention by them. So basically saying, okay, this word is so important to this other word. It has high attention. Therefore, you gotta have a bigger vector. Well, the vector's angle will go towards that. It will be biased towards that word. Basically, it consumes most of it represents most of the meaning of that word if it has high attention. Okay, so that's attention. I mean, we can. I mean, it's everything I said just in one equation too. One thing I didn't say, your final representation is the sum of obviously all the attentions, right? so then you go ahead. So now you can have multiple heads. So this exact same process with the exact same sequence, can be done 8 times. In this paper, at least it was 8 times. Now there are ways to get rid of. You don't absolutely have to use heads, but you use one head. But if you use that, if you use headed attention, then what will you do is like looking at things from different perspective. Now, okay, I understood this meaning, but what if I thought about it again? What if I went away and I don't know, took a nap for 5 minutes and came back with a different? Would I interpret it differently? Right? Think about it this way. So these heads are all randomly initialized. There's no guarantee. Actually, there's we're almost sure that it will seldom ever end up being at the same representation, so they will have different representations. So your head is an entire network, right? Copied, but they're not going to look alike because their gradients are going to be different. There's going to be different random initialization for them, right? So they're going to be different. But when you add them together, it's very powerful. If you have used ensembling techniques, it's kind of similar. Okay, and there's just how to add these. You can concatenate all the representations of all the heads, and then have a final matrix to get your output representation. And that output representation can be used for classification or for whatever purpose you want to have. So the so I'm talking about. I don't think we need to go through this, but I think this part is important. So now you might say, can actually someone else? Okay, can actually someone guess what's missing? And so if I parallelize the entire network, right? Each word separately, having a representation. And then finally adding all of them up to get one representation for the entire network. If it's natural language, can you guess what's missing?
Sequence, context?
Yeah, sequence. To some extent, context as well. Well, the context is there. You know what everything, but you don't know how things relate to each other with regard to the order. You don't know. Let me put it this way: you don't know what exactly came before and after a word. Right? You don't have that grand sequential vision anymore. You know how things are related, but only directly, which is the point of attention. That's how we get rid of vanishing gradients. Or well, it doesn't get rid of vanishing gradient to that extent, to be honest. It's more about long distance dependency. That's how we can access words from a long distance. If you remember, in the videos, I did say sometimes in a paragraph, you have 2 words that are very relevant. It's just they're not immediately after each other. How do you want to capture that relevance? That will translate into you correctly translating a subject pronoun, right? Because you know if it's written, if it should be a he or she or they. Anyhow, so that long distance dependency is easier to capture in transformer architecture, but it doesn't have sequence. To add but I think it's unnecessary, to be honest. It's at least at this in this context, we can basically use a bunch of sinusoidal variables to get your sequence. So you have you can get your sign of each position in different cycles, right? And that will give you a good understanding of your entire sequence. Yeah. Yep.
Isn't the probability of these work on this particular
No probabilities. No probabilities. It's absolutely deterministic. So you have your position index, right? You're divided by 2i of the model dimension. Well, by 1,000 times 2i of the model dimension, and that I will change. Like,
so
that's your
just
index.
the weight of this particular word.
It's sine and cosine. It's a combination. If it's a few sine and cosines, values of an index with different periods. right? Why do you need different periods? Because you want to see. I don't remember. I don't think I have the visual here, but you want to see. You want to look at different patterns of sequence. So in that way, it's just a way to encode your entire sequence and be sure that I got my entire sequence right. I can guess this word representation. So these values get added. Do I have it here? Yes. So these values get added to your vector
So
and
it's
applies to your
kind
vectors.
So the ranges between words in this particular sequence.
Exactly. Yeah. So you're technically encoding how these words actually like where they if you draw a line with this cosine and with this sinusoidal waves, you can make with a few of them. So you have a few of these waves. At each point, you can say where exactly that word occurs with underline.
Okay.
That's all it is. We can, if you want, talk to me after about the math, but that's one way to encode it. You can encode these things categorically, but I do not prefer that. Yeah.
With the sign though, like wouldn't it be kind of like the distinguishment between each positions might be really small because the numbers are so huge, like 10,000 whatever to the power of 2 or whatever.
Yeah.
Yeah. So if you're dividing it by a very large number, then that might cause like.
So that's why
not
you get
much of a distinguishment between two positions, right?
Right, exactly. That's why you get a few periods, right?
Okay.
So you get a range. You get different cycles. Right. Okay, a very good question. So, but basically, we add them to the vector representations. That's why we create these things. We want to be able to add to representations so that it can couple with the rest of the training. Otherwise, it's a deterministic thing. How do we incorporate it in our learning algorithm? So we added the vectors. Okay,
So,
and yeah.
In what moment we will add it?
Oh, good question.
Or
yeah, so they get added right when you generate the embeddings. So input, then you get your embeddings. Right away, you add the positional encoding. Right. Very good question. Thank you.
Just a quick, maybe dumb question.
Yeah.
The keys and values are they associated with the token, like the word? So here's an example. I took my luggage to the luggage drop-off counter. Right. So the word luggage appears twice, different contexts.
Right.
One's a noun.
Exactly.
One's an adjective.
Exactly. Yes.
Are the keys and values associated with that word the same?
No.
Positions?
No.
Okay.
They're different. Very good question. Because you're representing like they are in a different place in your sequence. They're in a different. So when you create the entire network, you have an input size that has a cap. Each input size is indexed, and for each you would have a separate key and value. If they happen at the same time, they're probably gonna, like if they're the exact same word, they're probably gonna have similar representations, probably, but there are gonna be differences because they're happening in different contexts. So they're absolutely different. Great question. Okay, nice. Okay.
So one quick question.
Oh,
so still at this point we are having different vectors for each word, right? We are not aggregating them together.
So we did, but I kind of glossed over it. So after, remember you have 2 layers. So you add your non-linearities,
Okay.
right? And what have you. And also you do your layer norm and skip connections, okay? And at the end, you end up with a representation called Z. Over here, right? So you put all of these. So you have I think it's before. This is with the attention heads. So at each layer, you input a vector of size Z, and you output the vector of size Z. Z1 over here. Then what's going to be different? It's another layer being processed, right? So and now you can use. So if you just add these Z's together for all the words, you get a representation of your entire sequence. And you can ask them, the position gets lost? No, because we just added the position encoding, right? But you don't have to add them. We add them here. You don't have to add them. You can use them however you want to use them. But it's easy to just add them and then either classify or regress. That's usually the end goal of this. Unless you want to generate a representation and just do, as I said, some sort of cosine distance. Okay, last, I'm very happy we got here. So last part is so we talked about the encoder and decoder, but I'm going to talk a tiny bit about decoder. But before that, how do you encode your vocabulary? Should they be? So we took it kind of for granted that they should be words, right? But if it's words, languages have tens of at least each speaker of a language, age, I don't know, 18, at least have tens of thousands of vocabulary in their active mind. Like if you speak of them, they immediately recognize the word and they interpret the meaning. They have even more, non-active vocabulary. That if you say something to them, they may get what it means still. So this vocabulary size is huge. How do you? So and it's a problem because it makes your matrices bigger, especially if you want to generate a word. So when you want to generate in your decoder, when you want to generate a word, if you have a very big vocabulary, you want to see the probability distribution of it for the entire vocabulary, right? 30,000 words. So that layer is a big layer, right? And it's a bottleneck in a lot of NLP applications.
So in this context, when you're saying generate a word, you're predicting what the next word is.
For example,
other examples would be
producing an entire summary,
okay.
Or producing a translation.
Okay.
Producing news, answering a question. Right. For all of these, you need to generate words. Right. And if it's big, it's a big problem. Right. But there's alternatives. We can use characters, 26 for English, and probably more. But it's never close. If you use the entire Unicode, you don't get close to what's the entire Unicode? 2 to 8.
Yeah, it's like
2.
So I wanted to ask you this question because I'm running this problem at my work right now.
Oh, okay.
So I was doing some sort of character embedding technique, and so like looking at UTF-8, it's about like 1 million. I think the range is about 1 million possible Unicode values.
Yeah.
So then like, of course that encoding space is huge.
It's huge, yeah.
Yeah, so I'm not exactly sure like how to necessarily reduce that. Maybe you just dependent on.
Let me steal your point because you gave me the number I was looking for, and finish my point and then get back to you.
Sure.
That's a very good question though. So for a character you don't have to use until for the purpose of what we're dealing with right now, transfer network, you don't have to encode the entire UTF-8, for example. Just get the characters of a certain language, right? And the alphabetic characters are around 26. If you add numerics to it, 10 more. It's in Arabic numerics. But regardless, that's much smaller than your. And the issue with that is that it's going to perform lower because characters have less information in them, arguably, than words. If I say to you T, you probably get less meaning out of it than, I don't know, I tell you T-Rex, for example, right? Anyhow, so here, we can use a different encoding method called BPE, bypair encoding or bypair coding. Where you use a combination of both. But before I get into the detail of that, and that performs well, and also doesn't have as big as a vocabulary as X. I'll get to that in a second, but let's address our friends. So you have what do you want to do? So you have
so like for example, like if you have a brand detecting multiple types of brand or something like that, and say for you have a misspelling in that brand, and like this is like for fraud, right?
Gotcha.
So like if that misspelling is say for that misspelled character is is some other character within the Unicode regime. So sort of where you replace PayPal, you replace the P with like a row sign.
Yeah.
So then that creates a larger embedding space. So I'm not exactly sure how to manage that.
Right. That's a very interesting problem to have. Usually people's encoding problems are messier than that. It's just their text has like multiple encodings in them. It's so hard. Okay, so there are two solutions to that. The simpler solution is what you were thinking. I think you were thinking of having some sort of embedding for the characters. Is that what? Did you already do that? Try that? Or?
The only thing is that the embedding size is like huge, right? Because then, I mean, theoretically, but of course, like maybe practically, I can limit the embedding size. Like, I can limit the number.
So you're saying the softmax is huge. So if I want to, but do you want to predict when you say it's huge? You're talking about what? Because
like say for you classify whether something is the brand or not the brand. Like,
you're saying that even the embedding matrix is big. So
yes.
I see.
Yeah. I continue with the same question. I mean, the same problem. So if we, as a human does, every human does. So if we have a question, we have a limited set of answers in our mind to choose from. So we don't choose the word from the whole vocabulary. We choose the answer pattern and then choose the words from this pattern. So it could be split it on or make it on different layers, and then.
So what you're saying translates into domain-specific algorithms. So if you're Google, you have to translate. Like if I'm speaking computer science, you got to translate. If I'm speaking religion, you got to translate, right? If you're Google, so it has to be general. So not everyone has the luxury of focusing on a domain, right? But what you're saying is that you can create a domain, a subdomain algorithm, train it on the subdomain, and have it only produce certain words. The issue, the only issue over there, and it's a trade-off. You get something, you lose something. Is that your text won't be just as large because you kind of restricted it to a single domain. And usually bigger data, like we hopefully won't use the entire internet to train. So again, I'll give you a quick answer for now, and then you can ask me about the details. Two ways. If you want to do it brute force, get a very big sort of, because what the issue is, it is processing, but it's mostly memory. You have a very big embedding vector, right? If you can get very big memory and get a cluster, you should be able to tackle that with clusters in EMR. You don't have to use GPUs. And you can use things like word-to-vec or character-to-vector to tackle that. So that's one way, but that's just brute force. The other way is you can use some sort of. Did I talk about hierarchical softmax?
I think
I talked into one of the videos.
Yeah, you have a.
Oh, I gave you material to study the details. Okay, so you can use hierarchical softmax to make to bring down the computation size or the computation cost, basically by the log of whatever it originally was, because it's a binary tree, right? And that makes the prediction easier. It doesn't get rid of your big matrix; it gets the prediction easier. But basically, two ways: get the prediction, output smaller, get your softmax layer smaller, or get your embedding size kind of smaller in a way or other, or also add compute. But if you have questions, ask me after. Okay, great question. So how do we merge them actually? So not to lose meaning that much. Character is very good actually. Like it's good to have both all the time. To be honest, if you can have both embeddings and you're predicting something, have both, because character and subword information can really help in most languages. Unless the language is completely like the words are completely isolated. Some languages are very, very few. Okay, so you start with your characters. This is the algorithm. This is PPE. You start with the words, with the characters. Sorry, you only look at the characters. You don't care about the words. You go the first pass. You have a frequency of characters, right? And then you look at two characters that co-occur the most with each other. Let's say these two characters. So for example, the distribution of words, if you're familiar with the Zipf's law, is so ridiculous. Like 50%, I think, of the words in a corpus are, and you have the methods to do this type of studies right now. You can just check, see what's your highly frequent word. It's usually either the or a, and that's like 50% of your entire corpus, right? And that's massive. So I better encode that, right? If you're familiar with entropy, you want to give the least bit of information to that, because you're going to do that all the time. You don't want to have 8 bits only for this thing. Anyhow, so you want to have a small size associated with that encoding. So you did it once, right? You got now you have an entire char set, in addition to one bigram, quote unquote. Bigram means just as 2 chars together, right? It can also mean 2 words together. Okay, let's do it again. What's the other bigram? And you do it for all the bigrams that are highly frequent, right? And then you move on to trigrams. You add them, right? And you can have a threshold to stop. Like where should I stop? Like this is my size. This is when I want to stop. The rest I don't care about. I already captured the most of the information by the least number of bits. I don't have to add anymore. The rest, you still have chars, remember. So you're not losing anything if you don't add to your vocabulary. Get the vocabulary to manage its size and use it, and that usually outperforms everything. I mean, it doesn't necessarily outperform words, but it could. But it definitely outperforms in terms of computation time. Okay, let me now talk about generation. Not all of you are gonna face that. I'll cover that in the videos. You'll have more videos come up. I'll see how you have the context. So I'm not worried about getting to you in time. It's just a more detailed sort of version of what I'm talking about today. You may have them in a couple of weeks or more, but you'll have access and you'll always be able to use them. But you have everything to do whatever you want to do today. So okay, thank you for your attention. How long do we have till break? 15 minutes? Okay, so let's leave it at the questions and then give you the first notebook to start working on. Let's start with the nonlinearity. So, okay, which one? Okay, let's start with text classification. Nonlinearity is less important. So let's start with the text classification. I shouldn't have said text classification. It's a news classification, news type classification notebook, right? We give it to you. So the link should already be online. So take a look at the news classification notebook. Meanwhile, if you have questions, please ask. If you don't have questions, just start a notebook. The notebook should be very self-sufficient. Any questions, you can ask me or the TAs.